Before you continue listening, find a comfortable place to lie down. Close your eyes and let your body sink into the surface beneath you. Let your mind ease and focus on the soft sounds around you. Imagine yourself resting as you listen to this quiet exploration of a question that has fascinated humans for centuries. Will we ever travel at the speed of light? Could a human ever move as fast as a beam of light? This question sits at the edge of our understanding of the universe. Light travels at a speed of roughly 299,792 kilometers per second, or about 186,282 miles per second. This speed is the fastest anything can move in the universe, according to our current understanding. Light travels effortlessly through the vacuum of space, moving faster than anything we have ever made. It races from the sun to the earth in just over 8 minutes, crossing millions of kilometers without slowing down. Light is a form of energy that moves in waves. It is part of what scientists call the electromagnetic spectrum. When we see colors, what we are actually observing is light with different wavelengths. Red light has a longer wavelength than blue light. Beyond what our eyes can see, light includes radio waves, microwaves, ultraviolet rays, X-rays, and gamma rays. All of these travel at the same speed in empty space. The consistency of light speed is what makes it unique and fundamental to physics. People have tried to measure the speed of light for hundreds of years. Early experiments were simple, using lanterns and mirrors, trying to measure how long it took light to cross a known distance. In the late 1600s, the Danish astronomer Ole Rømer noticed that the moons of Jupiter appeared to move slightly differently depending on where Earth was in its orbit. From this observation, he estimated the speed of light, showing it was not infinite, but a very large number. Later experiments, such as those by Hippolyte Fizeau and Albert Michelson, measured the speed more accurately, using rotating mirrors and precise clocks. Their work confirmed that light has a finite speed and helped define modern physics. The speed of light is not just a number, it is a limit in the universe. According to Albert Einstein's theory of special relativity, nothing with mass can reach this speed. As objects move faster and get closer to the speed of light, time for them slows down compared to observers at rest. Distances in the direction of motion appear shorter. Energy is needed to keep accelerating a mass, and the closer it gets to light speed, the more energy is required. Eventually, the energy required becomes infinite. This means that for anything that has weight, reaching light speed is impossible. Light, however, is different. Light is made of particles called photons. Photons do not have mass, and this allows them to travel at light speed naturally. They are not limited by the rules that apply to objects with mass. When we see sunlight, we are observing photons that have traveled across space for over 8 minutes. The same is true for distant stars. Some of the light we see tonight left stars thousands or even millions of years ago. These photons do not slow down. They always move at the same speed, unaffected by gravity or other forces in empty space, except in extreme cases where light bends around massive objects. To understand why mass prevents light-speed travel, imagine trying to push a car to faster and faster speeds. The faster it goes, the harder it becomes to accelerate. For a spaceship, the same principle applies. The closer it gets to light speed, the more energy is needed to increase its speed even a little. If it were possible to reach the speed of light, the energy required would be infinite. In other words, The laws of physics prevent any object with mass from ever reaching this ultimate speed. Even if humans could find ways to reduce weight or use enormous amounts of fuel, these limits are unavoidable. In laboratories on Earth, scientists accelerate tiny particles close to light speed in machines called particle accelerators. Protons, electrons, and other particles can reach over 99.999% of light speed, but they can never actually reach it. As they approach this limit, the energy needed to push them faster grows without end. These experiments confirm what theory predicts. The speed of light is a cosmic boundary. Light speed also determines how quickly information can travel. Signals, whether radio waves or data transmissions, cannot go faster than light. This has consequences for communication across space. Even if we had a perfect spacecraft, messages sent to other planets or stars would take years or centuries to arrive. The vast distances in space make the speed of light an essential limit, shaping everything from space exploration to the observation of distant galaxies. Understanding light speed also gives us insight into time itself. Clocks in satellites, such as those in the GPS network, must account for the way time changes at different speeds and gravitational strengths. Without correcting for these relativistic effects, GPS coordinates would drift by several kilometers each day. In these systems, practical engineering meets the fundamental limits imposed by the speed of light, showing that even in everyday life, we experience its influence quietly and constantly. In the largest laboratories on Earth, scientists use rings of metal called particle accelerators to push tiny particles to incredible speeds. Protons and electrons circle these rings millions of times per second, guided by strong magnets and electric fields. As they gain speed, their mass effectively increases, meaning that more and more energy is needed to continue accelerating them. Even with the most advanced technology, these particles can approach but never reach the speed of light. Observing them helps researchers understand how matter behaves under extreme conditions and confirms the predictions of Einstein's equations. Beyond our planet, the universe itself produces particles moving at nearly light speed. Cosmic rays, for example, are high-energy particles that travel across galaxies. Some are protons, others are heavier atomic nuclei, all moving at velocities so close to light speed that time itself slows for them. When these particles hit Earth's atmosphere, they create showers of smaller particles that scientists detect with special instruments. These natural experiments allow humans to study light speed effects without building machines on Earth. They show that even in the vastness of space, the laws of physics remain consistent. When we think about traveling at light speed, energy is always the main challenge. For a spaceship to move faster and faster, it must carry enough fuel to generate the enormous energy needed. But the faster it goes, the more energy it needs, and the amount grows faster than we can easily imagine. Even if we had fuels far more powerful than anything on Earth, the energy required to push a ship near the speed of light becomes unimaginably large. This is not just a practical problem. It is a fundamental one. The universe's rules make it clear. Objects with mass cannot reach light speed. Time behaves strangely as speed increases. Astronauts moving close to light speed would experience time differently from people on Earth. For them, a journey that seems short might last many years for those left behind. This effect, called time dilation, is not science fiction. It has been measured in experiments with atomic clocks flown on airplanes or placed in orbit. Even tiny differences in speed produce measurable changes in time. If humans could travel at extreme speeds, these effects would become enormous, showing that speed and time are deeply connected. Light itself reacts differently when it passes through materials. In air, water, or glass, light slows slightly. This does not violate the universal speed limit because the photons are absorbed and re-emitted by atoms in the material. The ultimate speed in empty space remains constant. This constant speed is what allows scientists to calculate distances across the solar system and beyond. By measuring the time it takes for light to travel, we can understand the vast spaces between planets, stars, and galaxies. Even with all these limits, humans continue to study ways to explore space more quickly. Rockets today are much faster than the earliest rockets, and engineers test new methods like ion drives or solar sails. Ion drives push spacecraft with gentle but continuous force, allowing them to gain speed over long periods. Solar sails use light itself for propulsion, capturing momentum from photons. While these methods increase speed, they remain far below the speed of light. They do, however, teach us about the physics of motion, energy, and space travel in the real world. Some ideas in physics explore shortcuts through space without breaking light speed. Rules. For example, the shape of space can bend near massive objects. Light and matter can follow curves in space-time, allowing paths that are shorter in distance than they seem. This bending does not let anything exceed light speed locally, but it changes the route traveled. Observing such effects around stars or black holes helps scientists test the predictions of general relativity and better understand the structure of the universe. We also see the effects of near-light speed motion in cosmic phenomena. Jets from black holes, for instance, shoot particles outward at speeds approaching that of light. Supernovae explode, sending material across space with enormous energy. By studying these events, astronomers witness nature performing experiments that humans cannot reproduce. These observations deepen our knowledge of physics, showing how energy, mass, and light interact at the extremes of the universe. In every case, the evidence points to the same conclusion. While light travels at the ultimate speed, objects with mass cannot. The closer they get to that limit, the stranger the effects become. Time slows, distances contract, energy demands skyrocket, and acceleration becomes harder. These are not just theoretical limits. They are confirmed in experiments, observations, and measurements throughout the cosmos. They form the framework that governs motion, energy, and the flow of time. One way scientists see the effects of moving close to light speed is by studying particles called muons. Muons are similar to electrons, but heavier, and they are created when cosmic rays hit Earth's atmosphere. On their own, muons decay very quickly, often in just a few millionths of a second. Yet many of them reach the ground before disappearing. This happens because the muons are moving so fast that time for them slows down compared to time on Earth. From our point of view, they live longer, allowing them to travel farther. These experiments show time dilation in action and confirm the predictions of relativity in a way anyone can measure. Satellites orbiting Earth also demonstrate the influence of high speed on time. GPS satellites move quickly around the planet and are farther from Earth's gravity than we are. Both speed and gravity affect the passage of time, so clocks on these satellites tick slightly differently than clocks on the ground. Engineers must adjust for these differences to keep GPS accurate. Without these corrections, navigation errors would grow by kilometers every day. This practical use of relativity shows that the rules of motion and light speed are not abstract. They influence daily life. Even in particle physics labs, scientists watch tiny differences in time and speed. Experiments with electrons and protons reveal that the faster a particle moves, the more massive it behaves. Mass increases gradually as speed approaches the speed of light, making further acceleration harder. These effects are measurable and match the predictions of special relativity precisely. Every test confirms that reaching the speed of light is impossible for anything with weight, no matter how small or how energetic. Light can bend around massive objects, an effect called gravitational lensing. When light passes near a star or black hole, its path curves, sometimes creating multiple images of the same object. This bending happens because mass warps space itself, guiding the light along curved paths. Observing these effects gives astronomers another way to understand the relationship between mass, energy, and the speed of light. Even though light always travels at the same speed locally, its path can appear longer or shorter depending on how space bends. The vast distances of the universe further illustrate the limit of light speed. Signals from the nearest star, other than the Sun, take more than 4 years to reach Earth. From galaxies millions of light years away, the light we see tonight began its journey long before humans existed. These distances highlight that even if a spaceship could approach light speed, journeys across space would still require years, decades, or even millennia. The universe is immense, and the speed of light shapes our understanding of its scale. Even when humans send spacecraft far from Earth, they are always far below light speed. The fastest probe, moving with the help of gravity and advanced propulsion, travels only a tiny fraction of light speed. Interplanetary missions take months or years to reach their destinations. The gap between our current technology and light speed is enormous, showing that the cosmic limit is not just a distant theory, but a real boundary we cannot cross. Energy considerations continue to define the challenge. A spaceship with a single passenger would need a mass of energy far larger than the entire Earth to reach speeds close to light. Fuel, propulsion systems, and power supply all become impractical long before light speed is near. These limitations are not due to engineering flaws. They are a consequence of the structure of the universe itself. Energy, mass, and motion are linked in a way that makes light speed unattainable for any object with weight. When photons travel, they do not experience time or mass in the way we do. From a photon's perspective, if such a viewpoint could exist, the journey from one end of the universe to the other is instantaneous. For humans and any object with mass, however, time always flows normally, and energy limits prevent matching that speed. This difference between massless and massive particles defines one of the most fundamental rules of nature. Looking at light from stars and galaxies, we see the universe's history. The speed of light carries information across space and time. Telescopes detect light that left its source millions or billions of years ago. By studying this light, scientists can learn about the conditions, composition, and motion of objects far away. The speed of light, unchanging and constant, allows us to read the story of the cosmos itself, showing both the limits and possibilities of motion across space. Even if technology advances far beyond what we currently know, the underlying physics remains the same. No matter how clever we are, no matter how much energy we can generate, an object with mass cannot reach light speed. The rules are not arbitrary. They arise from the fabric of space-time, the nature of energy, and the structure of the universe. Humans can approach light speed more closely over time, but the limit is absolute. Every experiment, observation, and calculation confirms it. In the universe, some of the most energetic events involve particles moving near the speed of light. Jets from black holes shoot matter outward at incredible speeds. These streams travel for thousands of light years, carrying energy far beyond anything humans can create. Observing them helps scientists understand how matter and light behave under extreme conditions. Even at these high speeds, the particles never exceed light speed. Their motion confirms the limits set by nature, showing that no object with mass can cross that ultimate boundary. Supernova explosions also demonstrate near light speed motion. When massive stars collapse, they release enormous amounts of energy. Particles and light rush outward, racing through space. The fastest of these particles reach speeds very close to light. Scientists use special detectors to measure them and to learn how energy spreads through space. Each observation confirms that while matter can move extraordinarily fast, it cannot reach the same speed as light. These cosmic events act as natural laboratories, testing the rules of motion on a scale far beyond what we can achieve on Earth. Even black holes provide insights into the relationship between light and mass. Light cannot escape from the region closest to a black hole, called the event horizon. Gravity there is so strong that it bends the path of photons inward. Outside this boundary, light can travel normally, following the curved paths of space-time. Studying these effects helps scientists understand the structure of space, the limits of motion, and how mass and energy interact with light. No matter how extreme the conditions, the speed of light remains constant, and nothing with mass can reach it. Some ideas in physics explore shortcuts in space. Space itself can bend and stretch. In theory, a tunnel or bridge called a wormhole could connect distant points in space. Light would still move at its normal speed locally, but the distance traveled could be shorter along the curved path. This does not allow mass to exceed light speed, but it offers ways to think about moving across vast distances in less time. Scientists study these possibilities using mathematics and the known rules of physics. They remain purely theoretical, yet they show how the geometry of space relates to speed and motion. Energy, mass, and motion are always linked. The faster something moves, the more energy it has, and the closer it approaches light speed, the more massive it appears. These effects are not visible in everyday life, but at extreme velocities, they dominate. In particle accelerators, satellites, and cosmic events, the consequences of high speed are measurable. Time slows for moving particles, mass increases, and distances along the direction of motion shrink. All these factors enforce the universal speed limit. Even simple light itself behaves in ways that teach us about limits. When passing through air, water, or glass, light slows slightly. Photons are absorbed and re-emitted by atoms, making the journey slower than in empty space. However, in a vacuum, nothing changes. The speed remains the same. Scientists use this constant to measure distances to planets and stars. The predictability of light speed allows humans to understand the size of the solar system and beyond, giving perspective on the vastness of space. Looking at distant galaxies, we see light that left billions of years ago. These ancient photons carry information about the early universe. The speed of light ensures that what we observe is both a snapshot and a story of time and space. No object with mass could travel across these distances at the same speed. Even the fastest spacecraft or the most energetic particles fall far short. The light reaching our eyes reminds us of both the limits of motion and the vastness of the cosmos. Every calculation, every observation, and every experiment confirms that light speed is absolute. Particles can approach it closely, but infinite energy would be required to reach it. Massive objects will always remain below this limit. Nature does not bend this rule. The laws governing motion, energy, and time are consistent across the universe. From laboratories on Earth to cosmic events millions of light years away, the results are always the same. This knowledge does not diminish the wonder of travel or exploration. Understanding the speed of light helps humans design spacecraft, communicate across space, and interpret the universe. It shapes our ideas of time, distance, and motion. While we cannot reach light speed, studying it allows us to approach the limit intellectually. We can imagine what it would be like to move at incredible velocities, even if physically it is impossible. The speed of light sets the rhythm of the cosmos. Every particle, every signal, and every observation is bound by it. Energy, mass, and time respond to its constancy. Observing the universe at large or performing experiments on Earth reveals the same truth. The limit is firm, absolute, and universal. Our understanding of it is one of the greatest achievements of human thought. It guides exploration, frames science, and informs daily technology, quietly shaping life on Earth and our understanding of the universe. Even with all we have learned about the universe, humans remain far below the speed of light. The fastest spacecraft ever launched travel only tiny fractions of that ultimate speed. Rockets rely on fuel to push them forward, and each boost consumes enormous amounts of energy. Chemical rockets burn fuel quickly but provide limited acceleration. Ion drives offer gentle, continuous force, pushing a spacecraft slowly but steadily. Over months or years, these engines allow spacecraft to gain speed, but even then, they remain far from the cosmic speed limit. The laws of energy make near-light speed travel difficult. As a spacecraft moves faster, it requires more and more energy to continue accelerating. The closer it gets to light speed, the faster energy requirements rise. Soon, the amount of fuel or power needed becomes impossible to store or produce. These limits are not technological, they are fundamental. Even if humans could invent engines far more powerful than anything today, the rules of physics prevent reaching light speed. Radiation becomes another challenge at high velocities. Particles moving near light speed encounter cosmic rays and photons from the environment. These high-energy collisions can damage spacecraft and living beings inside. Moving faster increases the energy of impacts, making protection difficult. Nature sets limits on how fast humans and machines can safely travel, showing again that light speed cannot be reached with massive objects. Gravity also plays a role. Massive bodies like planets, stars, and black holes warp space around them. A spaceship moving near such objects experiences changes in time and space. Time can slow or stretch depending on the gravitational field. These effects, predicted by Einstein's theory of general relativity, combine with the speed limit to define the structure of motion in the universe. Observations of satellites, stars, and black holes confirm these effects precisely. Even if humans could survive the forces, the distances in space make light-speed travel impractical. The nearest star beyond the Sun is more than 4 light-years away. Even at 99% of light speed, a journey there would take over 4 years from the perspective of someone on board. Signals sent back to Earth would take the same time to arrive. The universe is vast, and the speed of light sets the scale for how long travel and communication take. Observations in particle physics show us the limits clearly. In accelerators, electrons and protons reach speeds approaching light. As they do, their mass increases, clocks measuring their motion slow relative to our own, and their energy grows immensely. No matter how much we push them, they never reach the speed of light. This repeated confirmation of theory in experiments is one of the strongest pieces of evidence that the cosmic speed limit is absolute. Light itself travels without mass, and photons are forever bound to move at the speed of light. Their journey is unaffected by energy limits in the way it affects matter. Observing light from distant stars and galaxies is like reading a story of the universe. Every photon tells us about motion, energy, and time, and about the laws that govern everything with mass. It moves fast, constant, and unchanging, while massive objects can only approach it. The constancy of light speed also affects technology on Earth. Communication satellites, data transmissions, and even GPS rely on the same principle. Signals move at light speed, setting the pace for information transfer. Understanding this allows humans to measure distances precisely and navigate accurately. Even at small scales, the universe's speed limit is a guiding force. It shapes how we explore, communicate, and understand space. Every cosmic observation, from jets and supernovae to gravitational lensing, confirms the same truth. Matter cannot reach light speed, while photons move effortlessly across space. Energy, mass, and time respond predictably to speed, ensuring the laws of the universe remain consistent. The more we study, the clearer it becomes. Light speed is absolute, and our understanding of it opens a window into the structure of reality. Even imagining near-light speed journeys provides insight. Concepts like time dilation, length contraction, and mass increase are not just abstract ideas. They are measurable effects that occur naturally for particles moving at extreme speeds. Humans can simulate these effects in laboratories or observe them in space, learning how the universe behaves at its fastest scales. The cosmic speed limit is a boundary we cannot cross physically, but it allows deep understanding of motion and time. In space, light speed effects are visible in many ways. Some of the fastest particles we know come from cosmic rays. These high-energy particles travel across the galaxy, moving so close to light speed that time for them passes slowly compared to us. When they collide with Earth's atmosphere, they create showers of smaller particles. Instruments on the ground and in space detect these showers, allowing scientists to study near-light-speed motion without sending spacecraft. These natural events confirm that the rules of physics apply everywhere, from the lab to the farthest reaches of space. Observations of distant galaxies also reveal the influence of light speed. The light we see left those galaxies millions or billions of years ago. This ancient light carries information about the history, structure, and movement of those galaxies. By measuring its arrival and properties, astronomers calculate distances, speeds, and energy. The speed of light allows humans to see the universe not as it is today, but as it was when the light first left its source. No spacecraft could match this speed to make the journey in the same time. Light provides a constant reference across the vastness of space. High-energy jets from black holes are another example. Matter falling toward a black hole can be ejected in narrow streams, at speeds approaching light. These jets stretch for thousands of light years and shine brightly across the electromagnetic spectrum. Scientists study them with radio, optical, and X-ray telescopes. Even at such extreme velocities, the particles never reach light speed. Their behavior illustrates the rules that govern all moving objects, showing that no amount of energy allows matter to exceed the cosmic limit. Even in more familiar space, satellites and spacecraft follow the same laws. Satellites orbit Earth at high speeds, and engineers must account for time dilation when synchronizing clocks. Spacecraft moving faster through the solar system experience subtle relativistic effects. Every measurement, adjustment, and calculation shows the same fundamental truth. Matter moves slower than light, and light always keeps its constant speed. These effects, while small in human experience, are essential for accurate navigation and communication. The interplay of energy and mass at high speeds is always evident. As velocity increases, energy grows quickly. The closer an object gets to light speed, the harder it becomes to accelerate further. Mass appears larger from an outside perspective, requiring more energy to continue moving faster. This relationship is not arbitrary. It is a built-in rule of the universe. Experiments with subatomic particles, spacecraft, and cosmic rays all confirm it repeatedly. Nothing with weight can reach the ultimate speed. Gravity bends motion in ways that combine with light speed limits. Massive objects like stars and planets curve the space around them. Light follows these curves, and matter moving near them experiences changes in path and time. Observing bending light around stars, a phenomenon called gravitational lensing, gives astronomers a tool to study distant objects. Even in these complex situations, the speed of light remains constant locally. The universe's laws hold, shaping both motion and observation. Even if humans developed new propulsion methods, the fundamental rules would remain. Solar sails, magnetic drives, and other technologies might allow spacecraft to move faster than today's rockets. They could approach larger fractions of light speed than ever before, but they will never reach it. Energy requirements, radiation hazards, and the limits imposed by mass ensure that light speed is unreachable for any object carrying mass. The boundary is firm, universal, and absolute. Looking outward, the vast distances of the cosmos emphasize the limits. A journey to the nearest star, Proxima Centauri, takes over 4 years at light speed. At the speed of our fastest spacecraft, it would take tens of thousands of years. Even if propulsion improves, the immense distances mean that light speed will always define travel limits across space. Information, exploration, and observation are shaped by this ultimate pace. Time and motion are deeply linked to light speed. Clocks moving close to light speed run slower relative to those at rest. Distances shrink along the direction of motion. Mass increases as velocity grows. These effects are measurable in laboratories and in space. They illustrate the structure of reality, showing that motion is never absolute, but depends on energy, mass, and the speed of light. Every observation confirms the consistency of these rules. Studying light speed also teaches about the flow of information. Radio waves, laser signals, and other forms of communication travel at the same speed. Space missions, astronomy, and even everyday technology rely on this constancy. Observing and understanding these signals allows humans to navigate, explore, and measure the universe accurately. The speed of light shapes the rhythm of all motion, linking the cosmos and human experience in a precise and unchanging way. When objects move very fast, close to the speed of light, they experience changes that seem strange but are predictable. Time for them slows compared to observers at rest. Distances in the direction of motion appear shorter. Mass grows as speed increases. These effects, called relativistic effects, are measurable for tiny particles in laboratories and for fast-moving satellites in orbit. Even though we do not experience them in daily life, they govern the universe at high speeds. They show that the faster something moves, the more the rules of motion stretch and shift, always keeping light speed as the ultimate limit. Every high-speed particle observed in accelerators or in space demonstrates these effects. Muons created in the upper atmosphere live longer than expected because time slows for them. Protons in particle colliders require enormous energy to approach light speed, and yet they never reach it. Even in cosmic jets, matter traveling at extreme velocities remains below light speed. These examples reinforce the principle that no mass can match the speed of light. Even small spacecraft moving through the solar system feel the effects subtly. Engineers must calculate trajectories and timing, accounting for the finite speed of light and the slight relativistic differences in clocks on satellites. These adjustments ensure that navigation and communication remain accurate. The same laws that govern distant stars and cosmic rays also apply to human technology. Light speed links the universe, large and small, from particles to planets. Radiation from space becomes more intense at high speeds. Particles moving fast encounter photons and cosmic rays with higher energy than when at rest. This radiation can damage electronics and living tissue, presenting another barrier to near-light speed travel. Humans must protect spacecraft and crews carefully, but the risks grow as velocity increases. The universe enforces its rules in multiple ways, combining energy limits, radiation, and relativity to prevent light-speed travel for matter. Even light traveling near massive objects shows subtle effects. Gravity bends its path and energy shifts slightly in what is called gravitational redshift. Observing these shifts allows scientists to measure mass, distance, and motion in the cosmos. Light continues to move at the same speed locally, yet its journey through curved space can take unexpected paths. Studying these effects expands our understanding of motion, energy, and the structure of the universe. Distance emphasizes the role of light speed. Signals from Mars take several minutes to arrive on Earth. From Pluto, the delay is hours. From nearby stars, it is years. These delays are natural consequences of the cosmic speed limit. No matter how fast a spacecraft travels, it cannot escape these delays completely. Light sets the pace for travel, observation, and communication across space. Understanding this pace allows humans to explore effectively, even while remaining far below light speed. Energy, mass, and motion remain linked at all scales. Every increase in speed requires more energy. Every approach toward light speed increases mass and makes acceleration harder. Even with new propulsion technologies, the limits are firm. Solar sails, ion drives, and magnetic propulsion can bring improvements, but they cannot overcome the laws of physics. The universe enforces these limits consistently, showing that speed is always bounded by light. Looking at the cosmos, we see light that traveled for billions of years. The universe is vast beyond comprehension, and the speed of light defines its rhythm. Observing distant stars and galaxies is like reading a history book. Light allows us to know how matter moved long ago, how energy was released, and how structures formed. No human-made object can travel as fast as these photons, yet understanding them brings insight into the rules of motion, energy, and time. Even imagining near light-speed travel is instructive. If a spaceship could move close to light speed, time for the crew would slow. Distances in the direction of motion would shrink. Energy requirements would grow immensely. These predictions are not speculation. They are grounded in observation and theory. They demonstrate the consistent behavior of the universe, showing that light speed remains an unbreakable limit, while offering a glimpse into the strange and fascinating consequences of high-speed motion. The speed of light is a quiet, guiding principle. It defines motion, time, and distance. It shapes cosmic events and human technology alike. Even as humans dream of exploring the stars, light reminds us of boundaries, while also providing a lens to understand the universe. Every particle, every photon, and every spacecraft obeys the same law. The constant speed of light connects all scales of reality, quietly setting the pace of the cosmos and the rhythm of motion. Imagining near light speed travel reveals how different the universe becomes at extreme velocities. Time slows, distances shrink, and mass grows as speed increases. Even if a spacecraft could reach 99% of light speed, the journey would feel shorter for those on board, but much longer for those left behind. This difference is not just theory. It has been measured in experiments with fast-moving particles and precise clocks. The universe responds consistently, showing that motion is relative and that light speed remains a constant boundary. Observing distant stars and galaxies illustrates the influence of light speed on our perception of space and time. The light reaching Earth today may have begun its journey millions or even billions of years ago. In that time, galaxies have moved, stars have exploded, and cosmic structures have evolved. Our view of the universe is a record of past events, and the speed of light sets the pace at which this history arrives. No matter how fast a spacecraft might travel, it could never overtake these photons or see events unfold in real time across such vast distances. High-energy cosmic rays further confirm the universal speed limit. These particles travel through space at velocities very close to light speed. When they enter Earth's atmosphere, they produce showers of secondary particles, detectable by instruments on the ground. Their behavior matches predictions made by relativity. Even in these extreme natural conditions, matter cannot surpass light speed. Observing them provides evidence that the rules we measure on Earth apply throughout the universe. Jets from black holes demonstrate the incredible energies in the cosmos. Matter falls toward the black hole and is ejected in narrow streams at speeds approaching light. These jets stretch across thousands of light years, emitting radiation across the electromagnetic spectrum. Despite the immense energy involved, the particles in the jets remain just below light speed. their motion confirms that mass, energy, and velocity are linked in a predictable way, governed by universal principles. Even within our own solar system, light speed sets limits. Signals from Mars take several minutes to reach Earth. Communication with probes at the edge of the solar system may take hours. These delays cannot be eliminated. They define how quickly humans can send commands, receive data, and explore distant regions. Light acts as a natural timer and messenger, guiding exploration while enforcing the ultimate speed limit. Radiation hazards grow as speed increases. Any spacecraft moving close to light speed would collide with cosmic rays and interstellar particles at higher energies. Impacts would release intense radiation, presenting a major challenge for technology and life. The faster the motion, the more severe these effects. This natural barrier further prevents practical travel at or above light speed for objects with mass. Gravity shapes the paths of moving objects, even at high velocities. Light bends around stars, black holes, and other massive objects. Space itself curves under the influence of mass. Objects moving near these curves experience changes in time and motion. Studying these effects through gravitational lensing and satellite measurements allows scientists to understand both local and cosmic scales. Even in these warped regions, light speed remains constant locally, and no massive object can exceed it. Every observation, from particle collisions in labs to distant cosmic phenomena, confirms the same principle. Speed, mass, and energy are tightly linked. Approaching light speed requires more energy and increases mass. Time slows for the moving object. These rules are not suggestions. They are the framework of the universe. Nothing with weight can break through this limit, no matter the technology or energy applied. Even imagining futuristic propulsion highlights the same truth. Solar sails, magnetic drives, or theoretical antimatter engines could push spacecraft faster than today's rockets. Yet, despite increased velocity, they remain far below light speed. These ideas illustrate the challenge, teaching us about the interplay of energy, mass, and motion. Humans can approach the limit intellectually, simulating extreme speeds, but physical travel at light speed is impossible for massive objects. The constant speed of light quietly governs everything. It determines how we perceive the universe, measure distances, communicate, and explore. It shapes cosmic events and guides human technology. Observing the motion of matter, photons, and spacecraft shows the same pattern. Light moves at its constant pace, and mass can only approach it. In this simplicity lies a profound truth, linking particles, planets, and galaxies under a single universal law. Even on Earth, the limits of light speed influence our technology. Satellites orbit at high velocities, and engineers must account for tiny differences in time caused by their motion and gravity. GPS systems, for example, rely on signals moving at light speed. If the effects of relativity were ignored, positions could be off by kilometers in a single day. This shows that even small speeds compared to light produce measurable effects, reminding us that the universe enforces its rules consistently at all scales. In the vacuum of space, the speed of light also sets the pace for exploration. When humans send spacecraft to other planets, the delay in communication is a constant factor. Commands take minutes or hours to reach the craft, depending on distance. Data and images travel back at light speed, limiting real-time interaction. These constraints shape mission planning and define what is possible with current technology. They serve as a practical reminder that no matter the method, the cosmic speed limit governs every journey. Observing cosmic events highlights the consistency of light speed across the universe. Light from exploding stars, from pulsars spinning rapidly, and from distant galaxies travels uninterrupted for millions of years. Photons do not slow down, and their behavior is predictable. Matter, on the other hand, can only approach these speeds, never surpass them. By studying the arrival of light from different sources, astronomers understand motion, energy, and time across vast distances, confirming the same laws seen in laboratories on Earth. Even in particle accelerators, the principles are clear. Protons and electrons can reach 99.99999% of light speed, but require ever-increasing energy to move faster. Scientists measure their mass, velocity, and energy precisely, observing time dilation and other relativistic effects. Each experiment reinforces the conclusion: nothing with mass can achieve the ultimate speed of light. The rules observed on Earth apply to the farthest reaches of the cosmos, creating a consistent and predictable universe. Radiation remains a barrier to high-speed travel. At extreme velocities, collisions with particles in space release intense energy. These interactions could damage spacecraft and harm life, providing a natural limit to motion. The faster the object, the more severe the consequences. Nature enforces the cosmic speed limit, not only through energy and time, but also through the environment itself, creating multiple safeguards against breaking the universal rule. Gravitational effects continue to shape motion at high speeds. Massive objects warp space, bending the paths of moving matter and light. Observing light around stars or black holes reveals curved trajectories, time shifts, and energy changes. These effects are measurable and predictable, confirming that motion, energy, and time are interconnected. Even in warped space, light speed remains constant locally, and no mass can exceed it. The universe behaves consistently, whether at the smallest or largest scales. Distance emphasizes the role of light speed in cosmic perception. The nearest stars are years away in light travel time. Galaxies millions of light-years distant appear as they were long ago. Even if humans could travel near light speed, vast stretches of space would require years or centuries to cross. Light sets the rhythm of observation, ensuring that all events unfold at a pace that respects the cosmic limit. Information from across space reaches us in sequence, preserving the order of the universe. Energy, mass, and velocity remain tightly connected. As speed increases, energy requirements rise sharply. Mass increases for moving objects, making acceleration increasingly difficult. Even advanced propulsion systems, theoretical engines, or extreme energy sources cannot overcome these fundamental limits. Nature enforces the cosmic speed limit consistently, leaving humans with the challenge of understanding motion while respecting its boundaries. Considering futuristic travel emphasizes these points. Solar sails, ion engines, and hypothetical antimatter drives can bring spacecraft closer to light speed than current rockets. Yet, even these approaches remain below the absolute limit. They allow humans to explore faster, communicate across greater distances, and observe the universe more efficiently. But they do not change the fundamental rules. Light speed remains the unbreakable barrier for any object with mass. The speed of light is a constant rhythm that governs motion, time, and distance. It links the microscopic and cosmic, the laboratory and the farthest galaxies. Observing it provides insight into the behavior of particles, planets, stars, and spacecraft. Everything that moves, whether naturally or through human invention, does so under the same rule. This quiet consistency forms the foundation of understanding, guiding exploration, technology, and comprehension of the universe across all scales. When humans consider exploring the stars, the speed of light defines every possibility. Even the closest star outside our solar system is more than 4 light-years away. Traveling there, even at speeds approaching light, would take years for the travelers and longer for those on Earth. Communication with such missions would also be delayed, measured in years rather than minutes. The universe itself enforces these limits, shaping the scale and pacing of exploration. Every attempt to move faster encounters the same universal boundary, demonstrating the constancy of light speed. Observing distant galaxies shows the effects of time and distance together. Light travels for millions or billions of years before reaching us. When we look at these galaxies, we see them as they were long ago. Stars have formed and died, galaxies have shifted, yet the light still carries accurate information. This journey is possible because photons are massless, traveling at light speed. Matter, however, cannot achieve this speed. No spacecraft, particle, or person can outrun a photon. The distinction between massless and massive objects is clear and fundamental. High-energy phenomena in space reinforce this understanding. Cosmic rays, pulsar emissions, and black hole jets all involve matter moving near light speed. These particles carry immense energy, and observers can measure their velocity and relativistic effects. Time slows for these particles, mass increases, and energy grows, all while they remain just below light speed. These natural laboratories confirm the universal limit in ways human-made machines can only attempt to simulate. Radiation hazards increase with speed. Particles moving near light speed collide with interstellar matter and photons with tremendous energy. For a human spacecraft, these collisions could be dangerous, releasing radiation that would be difficult to shield against. The faster the craft, the more severe the exposure. Nature provides a built-in barrier, ensuring that massive objects remain below light speed. Even if energy and propulsion technology were sufficient, environmental hazards enforce the limit. Gravity affects motion for fast-moving objects. Massive bodies warp space, curving the paths of light and matter. Light bends around stars, and black holes, while moving matter follows the same rules. Observations of gravitational lensing and orbiting satellites confirm these effects with precision. Relativity ensures that light speed remains constant locally, and matter cannot surpass it, regardless of the energy applied. The universe behaves consistently, from the smallest particles to the largest galaxies. Even advanced propulsion cannot change these facts. Solar sails, magnetic drives, and theoretical engines could increase speed, approaching light but never crossing it. Energy requirements become extreme, mass increases, and time dilation becomes significant. Human technology may allow us to get closer to the limit, but the laws of physics maintain the boundary. Light speed is absolute, universal, and unbreakable for all matter. Distances across space emphasize the challenge. Traveling to the nearest star would take years at near light speed. Across the galaxy, journeys would take tens of thousands of years. Across the universe, billions of years. Light travels these distances effortlessly, carrying information about the past. Humans and spacecraft, bound by mass and energy, cannot match this speed. The scale of the cosmos is thus defined by light itself, shaping perception, travel, and exploration. Time and motion are inseparable at high speeds. Relativistic effects mean that moving objects experience slower time, increased mass, and shortened distances along the direction of motion. These effects have been measured with precision, both on Earth and in space. They are not theoretical ideas. They are real, observable consequences of the universe's structure. They ensure that light speed remains the ultimate limit, guiding all motion and energy in the cosmos. The speed of light quietly orders the universe. It governs particle collisions, spacecraft navigation, communication, and observation. From cosmic jets to GPS satellites, from distant galaxies to particle accelerators, the same principles apply. Light speed sets the rhythm for energy, motion, and time. Nothing with mass can reach it, yet its presence allows understanding, measurement, and exploration. Observing the universe through this lens gives humans insight into the laws that shape all existence. Even imagining journeys near light speed shows the strange and beautiful consequences of motion. Distances contract, time slows, and energy demands rise. Travelers would perceive a different universe than those at rest. Yet, despite these differences, the limit remains absolute. The constancy of light speed is a quiet but profound principle, connecting the micro and the macro, guiding exploration, and defining the rhythm of the cosmos. The speed of light shapes how humans see and understand the universe. Every signal, every photon, and every observation travels at this pace. When astronomers look at distant stars, they are seeing events that happened long ago. Light carries information about formation, motion, and energy across space. Even though spacecraft and human travel remain far below light speed, photons reach us steadily, giving a record of the cosmos. The constant speed provides both limits and guidance, shaping our comprehension of motion and distance. Time itself feels different near light speed. Experiments with fast-moving particles show that time slows for them compared to observers at rest. Clocks on satellites and in laboratories measure these differences. At everyday speeds, these effects are tiny, but at extreme velocities, they become significant. The universe enforces the same rule consistently, from tiny particles to massive spacecraft. Relativity ensures that light speed is the ultimate boundary, linking time, motion, and energy in one seamless framework. Distances in space appear vast because of this limit. Even the Moon is about 1 light second away. Mars, depending on its orbit, is several light minutes distant. The nearest stars are measured in light years, and the farthest galaxies in billions of light years. No spacecraft can cross these distances in the same time it takes light. The scale of the universe and our perception of it is defined by this constant. Light speed orders the cosmos, allowing humans to measure, explore, and understand it. Cosmic rays illustrate high-speed motion naturally. These particles travel near light speed across the galaxy. When they strike Earth's atmosphere, they produce showers of smaller particles. Instruments detect and measure them, confirming predictions made by relativity. The particles' behavior shows that, no matter how energetic, matter cannot reach light speed. Nature provides countless examples that reinforce this universal rule. Observing cosmic rays, is like reading proof written in the language of motion itself. Black hole jets provide another perspective. Matter falling toward a black hole can be ejected in narrow, energetic streams. These particles move incredibly fast, almost at light speed, stretching for thousands of light years. Their motion and energy distribution can be observed with radio, optical, and X-ray telescopes. Even in these extreme conditions, the particles never surpass light speed. Energy, mass, and velocity remain linked, and the universe maintains its rhythm consistently. Radiation becomes more dangerous at high velocities. Fast-moving objects collide with photons and interstellar matter with higher energy. Shielding spacecraft or protecting life in these conditions is a significant challenge. Even if propulsion could approach light speed, environmental hazards make the journey risky. Nature enforces its limits, not just through energy and time, but also through the physical conditions of space itself. These forces together ensure that light speed remains unreachable for massive objects. Gravity affects all motion, even for near-light speed objects. Massive bodies warp space and bend the paths of moving matter and light. Light curves around stars and black holes, and spacecraft experience slight changes in time and motion. Observations of gravitational lensing, orbiting satellites, and distant galaxies confirm these effects. Even in curved space, light speed remains constant locally, and nothing with mass can exceed it. The universe behaves consistently, from the smallest particle to the largest cosmic structure. Human technology, from satellites to particle accelerators, continues to confirm the limits. GPS systems must account for time dilation, and particle experiments reveal mass increase and relativistic effects. Observing high-energy particles in space, combined with these experiments, reinforces the conclusion. Light speed is absolute. Mass can approach it, but never reach it. Energy, time, and mass remain bound by this universal rule, shaping motion throughout the cosmos. Even imagining futuristic spacecraft provides insight. Solar sails, ion engines, or theoretical antimatter drives could push ships closer to light speed than current rockets allow. Yet these approaches remain below the ultimate limit. Energy requirements grow enormously, radiation hazards increase, and relativistic effects become extreme. Physics consistently enforces the rule. Light speed remains a boundary humans cannot cross physically, though understanding it allows exploration and knowledge to expand. Light speed quietly governs perception, motion, and measurement. It connects the very small with the very large, from particles in laboratories to galaxies, billions of light years away. Every photon, every signal, and every moving object follows the same law. Mass cannot reach light speed, yet light itself moves freely, carrying information and shaping understanding. This constant rhythm underlies all motion, linking the universe and human experience in a simple, yet profound way. The universe appears vast and slow when measured by the speed of light. Even light, the fastest thing in existence, takes years to cross the distance between stars. Galaxies millions of light years away show us the past, not the present. Every photon arriving carries a message from another time. Humans cannot travel this fast, yet by observing light, we can explore the universe across unimaginable distances. It shapes our perception, providing a steady guide through the immense expanse of space. Time and distance are connected by light speed. Moving objects experience changes that are not noticeable at everyday speeds, but become significant at high velocities. Mass increases, distances contract, and clocks run slower relative to observers at rest. These effects have been measured in laboratories with particles and in orbit with satellites. They show that the universe has built-in limits, and that light speed is the natural boundary governing the flow of energy and motion. High-speed particles in space provide natural laboratories for observing near-light speed effects. Cosmic rays collide with Earth's atmosphere, producing showers of secondary particles. These interactions reveal how time slows for moving matter and how energy and mass behave at extreme velocities. Even in these violent cosmic events, matter does not surpass light speed. Nature consistently enforces this rule, offering clear examples across space and time. Jets from black holes demonstrate energy and motion at the largest scales. Matter is accelerated to velocities close to light, traveling thousands of light years. Observations in radio, optical, and X-ray wavelengths reveal their structure and speed. Despite immense energy and acceleration, the particles remain below light speed. These cosmic phenomena illustrate the same principles observed in laboratories on Earth, showing the universality of the speed limit. Radiation hazards increase with speed. At near-light velocities, collisions with photons and interstellar matter release intense energy. For humans or spacecraft, these collisions pose risks. Protective shielding can help, but only to a point. Even with advanced technology, environmental factors limit travel near light speed. The universe enforces its boundary not only through physics, but also through natural conditions, keeping massive objects below the ultimate speed. Gravity shapes the paths of moving objects. Massive bodies curve space, affecting both light and matter. Satellites in orbit experience slight time shifts, while light bends around stars and black holes. Gravitational lensing allows astronomers to measure mass and distance. Even in these complex situations, light speed remains constant locally. No mass can surpass it. Observations confirm that the same rules apply from particle accelerators to the farthest galaxies, demonstrating consistency across scales. Human technology continues to reveal the limits. Satellites require precise adjustments for time dilation. Particle accelerators show mass increase and relativistic behavior at extreme velocities. Observing high-energy cosmic particles provides further confirmation. These measurements consistently support the conclusion that nothing with mass can reach light speed. The universe enforces this limit everywhere, from the smallest laboratory experiments to the largest cosmic structures. Futuristic propulsion may push human-made objects closer to light speed. Solar sails, ion engines, or theoretical antimatter drives could reduce travel time significantly. Yet even these approaches cannot overcome energy, mass, and relativistic barriers. Acceleration requires immense energy, radiation risks rise, and time dilation becomes extreme. Physics remains unbroken. The speed of light is the ultimate limit, and it cannot be surpassed by any method or technology. The constant speed of light quietly structures the universe. It governs motion, observation, and measurement. Photons move freely, carrying information across space and time. Mass moves slower, limited by energy and the laws of physics. Observing light from distant objects allows humans to explore, understand, and measure the cosmos. Light speed shapes every aspect of motion, from tiny particles to vast galaxies, linking all scales under the same rule. Even in thought experiments, near light speed travel shows profound effects. Distances contract, time slows and energy grows. Travelers would experience a different flow of events than those at rest. These consequences are not theoretical guesses, but measurable outcomes confirmed by physics. The universe maintains order through light speed, showing that motion, energy, and time are interconnected. In this quiet consistency lies the framework of reality, linking observation and motion across the cosmos. Looking outward, the vastness of space becomes clearer when measured by light speed. Stars, planets, and galaxies are separated by immense distances, each measured in light years. Light travels steadily across these gaps, carrying images and signals that tell the story of the universe. No spacecraft can match this speed, but observing light allows humans to explore regions far beyond their physical reach. The universe communicates through these photons, offering insight and guidance while maintaining its immutable pace. Time behaves differently for fast-moving objects. As velocity approaches light speed, clocks slow, and distances shrink in the direction of motion. Experiments with high-speed particles in laboratories and precise satellite measurements confirm these effects. Even if humans could travel at extreme speeds, they would experience the universe in a compressed way, while others would see the journey stretched over longer periods. The interplay of time, distance, and energy is a natural consequence of the cosmic speed limit. Cosmic rays provide practical proof of near-light speed phenomena. These particles arrive from distant sources, traveling close to light speed for millions of years. When they strike Earth's atmosphere, they create showers of smaller particles. Their behavior matches predictions from relativity, showing time dilation and energy-mass relationships. Observing these natural events reinforces that matter cannot exceed light speed, and that the rules governing motion are universal, applying equally across the cosmos. Black hole jets illustrate extreme motion and energy. Matter drawn toward the black hole can be expelled at near-light speeds, forming bright, narrow streams that stretch thousands of light years. Instruments detect their radiation across multiple wavelengths, revealing structure and dynamics. Despite the tremendous velocities, these particles remain below light speed. Their motion demonstrates how energy, mass, and velocity interact consistently, even under the most intense cosmic conditions. Radiation hazards increase as objects approach light speed. Collisions with photons and interstellar particles release enormous energy. Any spacecraft or life form moving near this speed would face intense exposure. Protective measures may help, but nature itself limits high-speed travel. Even with ideal propulsion, environmental conditions enforce the universal boundary. Light speed remains unreachable for massive objects, combining physical laws with natural challenges to maintain cosmic order. Gravity continues to influence high-speed motion. Massive bodies bend space, altering the trajectories of moving matter and light. Observations of gravitational lensing and orbital shifts confirm these effects. Even at high velocities, light maintains its constant speed locally, and massive objects cannot surpass it. The universe demonstrates consistency, from subatomic particles to the largest structures, showing the same laws operate across all scales. Human technology reflects these principles. GPS systems must correct for time dilation. Particle accelerators measure mass increase and relativistic behavior. Observing high-energy cosmic particles confirms the same rules in distant space. Experiments, satellites, and observations all point to a single truth. light speed is absolute, and matter cannot reach it. The universe follows these laws precisely, offering predictability and guidance for exploration. Theoretical propulsion approaches the same limit. Solar sails, ion engines, and antimatter concepts could allow faster travel than current methods. Yet even these remain below light speed. Energy demands increase sharply, radiation exposure grows, and relativistic effects intensify. Physics imposes the boundary consistently. Light speed cannot be broken, only approached. These limits shape human understanding of motion, energy, and exploration possibilities. Observing the cosmos through light teaches about scale and time. Light from distant stars shows the past. Photons carry information across immense distances, providing knowledge of formation, movement, and energy. Humans cannot travel as fast as light, but they can study it. The constant speed of light organizes perception, defines distances, and sets a rhythm for understanding the universe. It links the micro and macro, particles and galaxies, offering a quiet, steady order across space and time. Even imagining travel near light speed reveals profound insights. Distances contract, time slows, and energy requirements rise. Travelers would perceive a compressed universe, while observers see a stretched journey. These outcomes are measurable and predictable, confirmed in laboratories and through cosmic observations. The universe enforces its rules gently but firmly. Light speed sets the ultimate boundary, shaping motion, energy, and time. It provides a framework for understanding the cosmos, offering quiet clarity amid the vastness of space. The speed of light sets the scale for everything in the universe. Distances between stars and galaxies seem enormous, yet light crosses them steadily. Each photon carries information about its origin, whether from a nearby star or a galaxy billions of light years away. Humans cannot travel as fast, but by observing these photons, they can learn about cosmic events long past. Light gives a record of the universe, showing motion, energy, and structure over time and space. Time changes when objects move near light speed. Experiments with particles in laboratories, as well as satellites orbiting Earth, show that moving clocks tick slower. Distances also contract in the direction of motion. Even if humans could travel close to light speed, they would experience time differently than observers at rest. These effects, while subtle at everyday speeds, become significant at high velocities. The universe enforces these rules consistently, linking time, distance, and motion in a predictable way. Cosmic rays are natural examples of near-light speed travel. These particles travel vast distances at velocities close to light speed. When they strike the atmosphere, they create showers of secondary particles. Observations show time dilation and energy mass effects exactly as predicted by physics. No matter how fast they travel, these particles do not surpass light speed. Studying them helps humans understand motion, energy, and the universal limit in a real, measurable way. Jets from black holes provide insight into extreme velocities. Matter drawn in can be expelled in thin streams at nearly light speed, stretching thousands of light years. Observing their radiation across multiple wavelengths shows structure, speed, and energy distribution. Despite the tremendous velocity and energy, particles remain below light speed. These cosmic events demonstrate the consistent laws of energy, mass, and motion, reinforcing the universal boundary that governs everything with mass. Radiation hazards grow with speed. Fast-moving objects collide with photons and interstellar particles, releasing high-energy impacts. For humans or spacecraft moving near light speed, these collisions present serious risks. Shielding helps, but natural conditions still limit high-speed travel. Even with perfect propulsion, environmental factors enforce the boundary. Nature ensures that massive objects cannot reach the speed of light, combining laws and conditions to maintain cosmic order. Gravity affects fast motion subtly but significantly. Massive bodies curve space, changing the path of moving objects and light. Satellites experience small time shifts due to these effects, while light bends around stars and black holes. Observations like gravitational lensing confirm predictions with precision. Even at high velocities, local light speed remains constant. Nothing with mass can surpass it. The universe shows the same laws at all scales, from the smallest particle to the largest galactic structure. Human technology confirms these principles. GPS satellites account for time dilation to maintain accuracy. Particle accelerators measure mass increase and relativistic effects. High-energy cosmic particles behave as predicted, never exceeding light speed. These experiments, combined with observations, reinforce the universal rule. Light speed is constant, mass cannot reach it, and energy, time, and motion are linked in a precise, consistent way. Advanced propulsion concepts approach, but never reach, light speed. Solar sails, ion engines, and theoretical antimatter drives could accelerate objects faster than current rockets, yet they remain below the ultimate limit. Energy requirements rise sharply, radiation hazards increase, and relativistic effects become extreme. The speed of light cannot be broken, only approached. These boundaries shape human understanding of motion, energy, and the possibilities of travel. Light structures, perception, and exploration. Photons provide information across vast distances, allowing humans to study stars, galaxies, and cosmic phenomena. Spacecraft remain below light speed, but observing light bridges the gap, connecting distant regions to human understanding. The universe communicates through this constant speed, linking micro and macro, near and far, present and past, with quiet, reliable consistency. Even imagining near light-speed journeys highlights profound consequences. Distances compress, time slows, and energy demands grow. Travelers experience a different flow of events, while stationary observers see the journey stretched. These effects are not guesses. They are measurable and predictable. The universe enforces its rules gently, yet firmly. Light speed defines motion, energy, and time, providing a framework that guides understanding and exploration across the cosmos. The universe shows the effects of light speed in many ways. Signals from distant stars take years to arrive, showing humans the past. Light from galaxies billions of light-years away reaches Earth after a long journey, telling a story of formation, motion, and energy. Even though humans cannot travel at this speed, they can understand the universe by observing light. Photons act as messengers, carrying knowledge across space, while the universe itself moves at a steady, unchanging rhythm. Time behaves differently for fast-moving objects. Particles moving near light speed experience slower time compared to observers at rest. Distances shrink in the direction of motion. These effects have been measured in laboratories and in orbiting satellites. For humans, these changes are subtle at everyday speeds, but they become significant when approaching extreme velocities. The universe consistently enforces these rules, linking time, motion, and energy across all scales. Cosmic rays illustrate near-light-speed phenomena naturally. They travel for millions of years across the galaxy before colliding with Earth's atmosphere. These collisions produce showers of secondary particles, revealing energy-mass relationships and time dilation. Even at these extreme speeds, the particles do not surpass light speed. Observing them allows humans to study high-velocity motion and the universal limits without leaving Earth. Black hole jets demonstrate energy and motion on a massive scale. Matter is pulled toward the black hole and expelled in streams at velocities close to light speed. These jets stretch for thousands of light years and emit radiation that telescopes detect in multiple wavelengths. Despite their extreme velocity, particles never exceed light speed. Observing these cosmic phenomena confirms that energy, mass, and velocity are always linked, and that light speed is an absolute boundary. Radiation hazards increase at high velocity. Moving near light speed, particles collide with photons and interstellar matter, releasing intense energy. Any spacecraft or life form would face dangerous exposure. Even with perfect shielding, environmental conditions limit travel. The universe enforces the cosmic boundary through both physical laws and natural conditions, keeping massive objects below light speed. Gravity affects motion subtly at high speed. Massive objects bend space, curving paths of light and matter. Satellites experience small time shifts, while light bends around stars and black holes. Observations such as gravitational lensing confirm these effects. Locally, light speed remains constant, and massive objects cannot exceed it. The laws governing the cosmos are consistent, applying from the smallest particle to the largest galaxy. Human technology continually confirms these limits. GPS satellites must adjust for time dilation, particle accelerators measure mass increase, and cosmic rays behave as predicted. These measurements reinforce the universal truth. Light speed is constant, and matter cannot reach it. Energy, motion, and time are interconnected, forming a reliable framework that governs the universe. Futuristic propulsion can approach light speed but never surpass it. Solar sails, ion engines, or antimatter drives could accelerate spacecraft faster than current rockets, yet they remain below the ultimate limit. Energy needs increase sharply, radiation risks grow, and relativistic effects become extreme. Physics sets the boundary consistently. Light speed cannot be broken, only approached. These limits shape human understanding of motion, energy, and exploration. Observing the universe through light allows humans to perceive distant events. Photons bring information from stars, galaxies, and cosmic events far beyond physical reach. Spacecraft cannot travel as fast, but light bridges the gap. The universe communicates through photons, providing insight into motion, energy, and structure. Light speed gives order to space and time, linking micro and macro, present and past, in a quiet and steady rhythm. Imagining near light speed travel highlights remarkable consequences. Distances shrink, time slows, and energy requirements rise. Travelers experience a compressed universe, while stationary observers see stretched journeys. These outcomes are not hypothetical, they are real and measurable. Light speed defines the limits of motion, energy, and time. It provides a framework that governs exploration and understanding, quietly shaping the universe and guiding human insight across space. Light speed shapes not only travel, but also observation and measurement. Every photon that reaches Earth carries information about distant stars, planets, and galaxies. Observing these photons allows humans to reconstruct events that happened long ago. Even the tiniest detail, such as the movement of a star cluster, is recorded in light. This constant pace provides a universal ruler, a standard by which distance, time, and motion are measured, giving structure to the vast expanse of space. Time shifts occur naturally at high velocity. Experiments with particles show that as speed increases, clocks in motion slow down compared to stationary observers. Distances contract along the direction of movement. These effects, predicted by relativity, have been confirmed repeatedly. Even if humans could travel at extreme velocities, they would experience time differently than those at rest. The universe enforces these rules steadily, connecting time, energy, and motion in a predictable, observable way. Cosmic rays demonstrate near-light-speed motion across vast distances. Traveling for millions of years, they strike Earth's atmosphere with extreme energy, producing showers of secondary particles. These interactions reveal the principles of relativity in action. Energy increases, mass appears greater, and time dilates. Observing cosmic rays allows humans to understand near-light-speed behavior naturally, proving that nothing with mass can reach light speed. Nature offers countless examples that reinforce this universal boundary. Jets from black holes display high-energy motion across large scales. Matter falls toward the black hole and is ejected at velocities close to light speed, forming narrow streams that extend thousands of light years. Radiation from these jets is detectable in multiple wavelengths, revealing structure, speed, and energy distribution. Despite extreme velocities, particles never exceed light speed. Observing these cosmic jets confirms that energy, mass, and velocity interact consistently, demonstrating the universality of physical laws. High-speed travel increases exposure to radiation. Particles moving near light speed collide with interstellar matter and photons, releasing enormous energy. Any spacecraft or living organism would face severe hazards. Protective shielding can reduce risk, but cannot remove it completely. Environmental factors reinforce the natural limit. Even with perfect propulsion, massive objects cannot reach light speed. The universe maintains order through both physical law and natural conditions. Gravity influences motion subtly but profoundly. Massive bodies warp space, curving paths for light and matter. Satellites experience time shifts and light bends around stars and black holes. Observations of these effects, such as gravitational lensing, confirm predictions with precision. Locally, light speed remains constant, and massive objects cannot surpass it. From particles to galaxies, the same rules govern motion, demonstrating the universe's consistent behavior. Technology continues to validate these limits. GPS satellites adjust for time dilation to remain accurate. Particle accelerators measure mass increase and relativistic effects. Observations of high-energy cosmic particles show that light speed is constant. These findings confirm that energy, time, and motion are intertwined, and that the universal speed limit applies everywhere. Humans can approach it, but never exceed it. Futuristic propulsion brings objects closer to light speed than current methods allow. Solar sails, ion drives, and antimatter engines could increase velocity dramatically. Yet, even these approaches remain below the ultimate limit. Energy demands rise sharply, radiation hazards grow, and relativistic effects become significant. The laws of physics enforce the boundary consistently. Light speed cannot be surpassed, only approached. Understanding this rule guides exploration and deepens comprehension of the universe. Light organizes perception and knowledge. Photons from stars and galaxies carry information across immense distances. Spacecraft may travel slowly in comparison, but light bridges the gaps. Observing distant events through light allows humans to understand formation, motion, and energy. Light speed provides a quiet rhythm for the cosmos, linking the present and past, micro and macro, giving a structure that guides observation and measurement consistently across space. Even imagining near light speed journeys reveals profound truths. Distances contract, time slows, and energy requirements rise sharply. Travelers would perceive events differently from stationary observers, experiencing a compressed universe while others see a stretched journey. These effects are not theoretical. They are measurable and predictable. Light speed defines motion, energy, and time. It provides a universal framework, quietly shaping human understanding and the structure of the cosmos, linking observation with the flow of the universe. As humans look out into space, the speed of light remains a quiet guide. Every photon that reaches Earth carries information from the past, from stars, galaxies, and cosmic events. Observing light allows humans to explore the universe without moving at impossible speeds. It shows the structure of galaxies, the formation of stars, and the movement of matter across vast distances. Light reveals the order of the cosmos and the boundaries within which all matter must move. Even if humans could travel near light speed, the universe would still impose limits. Energy requirements grow immensely, radiation hazards increase, and time behaves differently for travelers. Distances shrink and clocks slow, yet mass cannot reach light speed. These effects are not imagined. They are real and measurable. They define the framework of reality, ensuring that motion, energy, and time remain consistent across the cosmos. From cosmic rays to black hole jets, from distant galaxies to particle accelerators, every observation reinforces the universal truth. Nothing with mass can exceed light speed. Gravity, energy, and motion interact in a precise balance, and the universe maintains its structure and predictability. Human technology confirms this, while natural phenomena provide vivid examples across space and time. Light speed quietly governs the rhythm of the cosmos. By understanding light, humans gain perspective. Distances, time, and motion are all measured against it. Spacecraft may move slowly, but photons travel across the universe steadily. Observation through light bridges the gap between what humans can reach and what exists far beyond. The constant speed of light allows comprehension of events from the smallest particles to the largest galaxies, connecting past and present in a continuous stream of information. Imagining travel near light speed illustrates the profound effects of the universe's rules. Travelers experience time differently, energy requirements grow, and motion is constrained by immutable laws. Even with the most advanced propulsion, the boundary cannot be crossed. This limit is not a restriction, but a guide, showing the consistency of natural law and providing a framework for understanding motion and energy. In the quiet vastness of space, light continues its steady journey. It carries the story of stars, galaxies, and cosmic events across billions of years. Humans observe, measure, and learn, gaining knowledge that extends far beyond physical travel. The speed of light shapes perception, exploration, and understanding. It sets a limit, but within that limit, it offers clarity, structure, and insight. Light speed defines the rhythm of the universe. It sets the scale of distance, the flow of time, and the limits of motion. Everything with mass must remain below it, yet light moves freely, connecting all that exists. Observing light allows humans to see the past, understand the present, and imagine journeys across space. In this constant, unwavering speed, the universe provides a framework that is at once simple and profound. Even without traveling at light speed, humans can explore the cosmos. By studying photons, observing cosmic rays, measuring relativistic effects, and understanding gravitational influences, humans gain insight into the order of the universe. Light provides a guide, a measure, and a record. It governs motion, time, and energy, allowing observation and comprehension across space and scale. As the universe continues its quiet motion, the speed of light remains the ultimate boundary. It cannot be broken, yet it allows exploration through observation. It structures the cosmos, guides human understanding, and connects the farthest reaches of space to the observer. Light speed shapes knowledge and perception, providing a constant rhythm that humans can follow with patience and care. In the stillness of the cosmos, the speed of light continues to flow, steady and unchanging. Photons carry stories from distant stars, revealing the universe in a continuous stream of information. Humans, grounded on a small planet, learn from this light, understanding motion, energy, and time. Light sets the limits, yet within those limits it illuminates everything, offering clarity and insight into the grand structure of the universe.